Good morning. Thank you for this kind presentation. Today, I'm going to present a part of the results I have achieved during my PhD study. This is a part of my PhD thesis, and we have just received a letter from an editor. We have this work accepted, and I'm really happy to share with you these new results. First, I would like to give you a definition of inflammation. I think that you can see my screen, but probably I need to...
Yeah, full screen.
Okay,
better.
Full screen now, okay.
Yeah.
So the inflammation is the natural response of your body when there is an external threat, for example, the presence of a pathogen. And in this case, your immune system activate a great number of pro and anti-inflammatory agents to eliminate this threat and promote a quick healing. So it is a protective mechanism of our body, and it is very complex, and sometimes dysregulation of this complex dynamics could damage healthy tissue and impair physiological function. Inflammation, indeed, is now recognized as the underlying basis of a wide range of chronic and debilitating disorders. For this reason, the complete knowledge of this process has become one of the biggest challenges in immunology. As easily expected, a great number of mathematical models of inflammation has been proposed. Since the process is very complex, generally each model describes only a particular aspect of the process. And in particular, a research group from Pittsburgh has proposed several models of acute inflammation, which is the first stage of this process, and probably it is the most important stage. And thanks to these models, they have proposed and also verified different hypotheses on the inflammatory process. But the majority of these models does not take into account the spatial aspect. Today, I shall present a spatial model describing the acute stage of inflammation and a study we performed to explore the mechanisms of this phenomenon. First, I will focus on a modeling aspect, and then I will present a study on the onset of stationary and oscillatory instability, I mean Turing and wave instability, which are able to reproduce persistent in time or recurrent inflammatory activity. I will show you that the model displays a rich variety of bifurcations in parameter regions in which they are not expected on the basis of the classical analysis. And then I will show you through a weakly nonlinear analysis the existence of radially symmetric solutions which are able to reproduce different skin-shaped eruption. All these results are supported by numerical simulations. And one of the most important aspects of this work is that in all analysis and simulations, we have adopted only parameter values taken from the experimental literature. In particular, I will show you that this model is able to reproduce different clinical scenarios when we change the parameter values within a range. First, I would like to briefly explain the biological system. I will explain a simplification of the biological system. It is well known that macrophages play a central role in during an inflammation. They are a family of immune cells living in all tissues of our body, but in a resting state. When there is a pathogen, for example, macrophages become activated, engulf the foreign body, and release signaling molecules, which diffuse in the tissue. In the first stage, they release a pro-inflammatory chemokine to activate other macrophages, and the newly activated macrophages move up the gradient of chemokine. So there is a chemotactic movement. In a later stage, they release anti-inflammatory cytokine, a molecule to quench the inflammatory activity. And this is very important, this anti-inflammatory behavior, because if the inflammation is prolonged too much over time, it can damage healthy tissue. So, taking into account this biological system, we have constructed our chemotaxis model. This is a recently proposed model. It consists of 3 populations: the activated immune cells, the macrophages, and the 2 types of signaling molecules, the chemokines and cytokines. And in this model, each term describes a precise mechanism acknowledged in medical literature, and the functional forms adopted have been experimentally verified. We have found all this information in literature. All 3 populations diffuse linearly in space, and in particular, macrophages are characterized by a chemotactic movement, which is described by this term here. And this function, the chemotactic sensitivity function, describes a very well-known phenomenon in biology. When the density of C increases, the rate of chemoattraction is reduced because the receptors above the surface of the macrophages becomes saturated, and it leads in a decrease in the rate of chemoattraction. And the validity of this function here has been experimentally verified. This term describes the activation of macrophages. As you may have noticed, in this model, there is not a pathogen triggering the inflammation. Here we assume that the initial insult is described by the initial condition. And here we decided to describe the activation of macrophages driven by inflammation itself. Indeed, it has been observed that macrophages and pro-inflammatory chemokines work together to amplify the inflammatory response, for example, by inducing damages on healthy tissues. It is a very well-known phenomenon in biology, and for this reason, the activation of macrophages is proportional to the product between M and C. We have also included a saturation term. M bar, which is the carrying capacity, is a constant, and here we assume that it is equal to the average density of resting macrophages, and there is a particular density in each tissue of our body. This term is one of the novelty of our model, because generally in models of acute inflammation, the number of activated macrophages is kept fixed. The molecules dynamics are the same. They are both produced by macrophages, and the presence of the anti-inflammatory cytokines reduces this production, because the cytokine inhibits the macrophage's activity, and it has been observed experimentally that it results in a reduction of both molecules' production. These are 2 linear decay terms. And finally, this parameter here is very important. Tau is always greater than 1, and describe the fact that the cytokine dynamics follow a slower time scale than the pro-inflammatory agent. We will see that this parameter is very important for the dynamics of the system. So we have analyzed this problem on both 1D and 2D spatial domains, imposing no-flux boundary conditions. And as I have already said, all parameter values and also ranges are taken from the experimental literature. Now I will show you the linear stability analysis close to the non-trivial equilibrium point of the system. Indeed, a non-trivial equilibrium point corresponded to a high density of macrophages, but high density of activated macrophages is a hallmark of an inflammatory activity which create, for example, a rash on your skin. So we would like to understand if this model is able to reproduce not only homogeneous rashes, but other classes of rashes. The model has a unique non-trivial equilibrium point, which corresponds to a homogeneous steady state in which all macrophages has been activated. As always, we can linearize the system about the equilibrium point, and looking for solution of this form, since we adopted Neumann boundary conditions, we get this eigenvalue problem. And the stability of the equilibrium point depends on the eigenvalues of A. And in particular, if all eigenvalues are positive, the equilibrium point is stable. If there exists one eigenvalue with positive real part, the equilibrium point becomes unstable. And since our system consists of three populations, we can have a Turing instability when the eigenvalue is real and positive, or a wave instability when it admits a pair of complex eigenvalues with positive real part. First, we have analyzed the system without diffusion and chemotaxis, and we have seen that the equilibrium point is always stable. Then we have included the linear diffusion terms, and we have proved that without chemotaxis, again, the equilibrium point is stable. This means that in our model, chemotaxis is the only potentially destabilizing mechanism. To study how chemotaxis can destabilize the equilibrium point, we have analyzed the characteristic polynomial, and we have used the Routh-Hurwitz criterion, which states that the point is stable if and only if these three conditions hold. In our case, n is always positive, and the violation of the second condition, regardless the sign of this quantity here, correspond to a single positive eigenvalue, which means that the system admits a Turing instability. And for any parameter choice, we have seen that there exists a threshold such that if chi is greater than this threshold, chi is the chemotactic parameter, then the system admits a Turing bifurcation. The violation of the third condition correspond to the existence of two eigenvalues with positive real part. This result is given by the Routh-Hurwitz criterion, but we don't know if they are complex or real. To have a wave instability, we need complex eigenvalues. And here I underline this fact because generally in literature, this condition here is used as necessary and sufficient for a wave stability to occur, but it is not completely correct. We need another condition to be sure that the system admits a wave stability. So we have proposed this criterion, which state necessary and sufficient conditions for a wave instability. The first two conditions are given by the Routh-Hurwitz criterion. The third one states that the determinant of the Bezutian matrix associated to the characteristic polynomial must be negative. This condition here ensures that the system admits a pair of complex eigenvalues. So, in this case, we are sure that the system admits a wave instability. The definition of the Bezutian matrix can be easily found in several algebra books. So, we have analyzed when the wave instability occurs, so in our system, because it is a general criterion. And we have seen that if the anti-inflammatory cytokine acts with a sufficiently slow time scale, which means tau is sufficiently large, there exists a wave instability threshold. So using this theorem and the previous one about the Turing instability, we have analyzed the instability regions in the plane tau chi. Above the red line, which does not depend on tau, we have a Turing instability, and in the gray regions, the wave instability. From the biological point of view, the analysis of the wave instability suggests that if the anti-inflammatory cytokine act with a sufficiently slow time scale, then a resolution, temporal and local resolution of the inflammation is possible. I will show you two numerical simulations. These are the spatio-temporal evolutions of the solution on 1D spatial domain in the Turing instability region and in the wave instability region. Here we observe that the solution evolves toward a stationary pattern, which is able to reproduce a persistent inflammatory activity. In this case, we have a recurrent inflammatory activity, and in literature, we have found some examples of recurrent inflammatory activity, and we have shown that it is possible to choose proper parameter values to reproduce the mean number of episodes per year. After that, we have analyzed the system far from the equilibrium in the Turing instability region, and we have discovered other kind of patterns. I will show you the results we have obtained by increasing the parameter chi in the Turing instability region. After the expected Turing pattern, by increasing chi, we have seen that the Turing pattern begins to oscillate, but these oscillations are not expected. And here on the left, I show the temporal evolution of the solution in a fixed point of the space domain in the space M, C, and A. We see a ring which enlarges as chi is increased, then a period doubling bifurcations before the onset of spatiotemporal irregular solutions. And it is interesting to observe that as chi is increased further, the solution becomes ordered again. So the system admits windows of irregular solutions immersed in ordered state. And we have analyzed the nature of these oscillations. This is the dispersion relation, and here we can observe that no complex eigenvalues are expected. Complex eigenvalue with positive real part, because we see some oscillations. So one would expect a pair of complex eigenvalue with positive real part, but this is not the case. So we have analyzed the Fourier spectrum of the numerical solution, and we have seen that we observe here the excitation of the Turing mode, which is 4, but also the excitation of the 1/2 Turing mode. This is unexpected because it is linearly stable. This means that far from equilibrium, the nonlinear interaction between the Turing mode and its subharmonics are able to generate oscillations in the solution. And you can understand, you can analyze the onset, also characterize the onset of these oscillations, deriving these amplitude equations, which describes the subharmonic interaction between the Turing mode and its 1/2 subharmonic to do so, you can use, for example, a central stable manifold theory. I will not give the details of this result. It's just to give you an idea. And finally, I would like to understand which is the mechanism that generate this unexpected behavior. And we have analyzed the problem without the activation term for macrophages. In this case, we have not seen oscillations and chaotic dynamics, but only metastability and coarsening dynamics. This means that the logistic term of macrophages drives the transition towards chaotic solutions. But we are dealing with a biological system, so we would like to understand which is the meaning of these chaotic solutions. The windows of irregular solutions reproduce criticality. A living system is said to be at criticality when it lives at the edge between ordered and disordered state, which are generated by stability and adaptability. And the criticality is the good balance between stability and adaptability. And a characteristic of critical behavior is the following. When there is a slight change in the environment, the living system shows unexpected, uncontrolled chaotic behaviors. So windows of irregular behaviors. And our system is able to reproduce these critical dynamics thanks to the inclusion of the activation term for macrophages. Now I would like to show you some interesting results on 2D spatial domains. I will show you that the system is able to reproduce an erythema annulare centrifugum, its temporal evolution on your skin. It appears on the skin as a small red spot, then it enlarges and the central area clears. The final configuration is a ring, more concentric rings, and sometimes inflammation appears again in the center of the ring. And to study the occurrence of these radially symmetric solutions, we have performed a weakly nonlinear analysis. Again, I will not give all details. We performed this analysis to obtain the amplitude equation, which gives us information about the type of solution we can expect. In particular, when the amplitude is positive, we have a so-called bump solution with a maximum in the center of the domain. When A is negative, we have the so-called ring solution. Moreover, we can analyze the stability of bump and ring solution thanks to the amplitude equation. The stability depends on the sign of L. The red line corresponds to stable solutions, the dotted line to unstable one. So thanks to this analysis, we can characterize which kind of solutions we can expect. Now I will show you some numerical simulations performed on 2D spatial domains. When chi is below the Turing threshold, the initial condition evolves toward a homogeneous rush. And the initial condition is a high localized density of activated macrophages. And we don't know the reason why these macrophages has been activated, okay? And the same initial condition when L is negative and chi is greater than the critical threshold show that the rash appears on your skin, enlarges, the central area clears. When L is positive, the same initial condition has the following evolution. So little rash, which clears in the center, and inflammation appears again in the center of the domain. The numerical growth rate is a good agreement with the measured growth rate. And we have also seen that high values of chi decelerate the formation of the rash, and high values of R accelerate the formation of the rush, and also promote the formation of more rings. In conclusion, today I have presented the mathematical derivation of a model of acute inflammation. The model admits both Turing and wave stabilities. We have proposed a new criterion to characterize the onset of a wave stability. We have shown that the system is able to reproduce a skin-shaped, ring-shaped skin eruption, and the model displays a rich variety of solutions due to subharmonic instabilities. This analysis finally suggests that the chemotaxis generate persistent or recurrent spatial aggregation of activated macrophages. That tau is necessary, a large tau is necessary for a recurrent erythema. R is able to generate critical behaviors, and we have seen how how the rush evolves as function of chi and R. Unfortunately, our model is not able to reproduce the resolution of inflammation, and we would like to propose in the future a model describing the late stages of the inflammatory process. We will also analyze in deeper detail the subharmonic instability, and finally the well-posedness of this problem, and because we are interested in local global existence and regularity of solutions. Thanks for your attention.
Thanks a lot, Valeria. That was very interesting. Let's see if we have any questions from our audience. There are some experts here. I see Poppy's here. I think Mark is interested. Yeah. Brenna's here. Okay. Okay, while perhaps people are thinking about it, can you, I guess one question that I have is, at some point you were talking about criticality, right? So you were saying it's sort of a balance between stability and adaptability. How do you actually measure it? How can you decide if some dynamics are critical?
Okay, it's not my job.
Okay.
In the sense that there are different techniques to understand if a living system is critical. For example, in this work here, they use some information theory to understand, to prove that macrophages dynamics are critical, but I have not the tools to understand if a system is critical. I just observe that my system is able to reproduce criticality.
Right. I see. But when you're talking about stability here, I mean, there are so many different notions of stability, right? So what can be too much stability in this sense? Are we talking about some sort of, I mean, okay, even in the linear setting, right? So you're talking about some asymptotic stability, I suppose, right? So basically yes, negative.
Yes, but in this case, stability has a different meaning. Okay. Here, stability means that the living system wants to be ordered, wants to keep its ordered structure. It's not the mathematical stability here. I see. Okay.
But again, it has to be reflected in the dynamic somehow, right?
Yeah, sure. Yes, because if, for example, we have a stable equilibrium point in our system, yes, it is able to reproduce the stability with this meaning here. Yes.
I see. Okay. All right. Thank you very much.
Thank you.
We have one more minute, and if nobody else wants to ask a question, I have another one.
Okay, good.
So my question has to do with the initial conditions. For example, if you try to reproduce the rings that we saw on the skin towards the end, right? So you need to prescribe some sort of, I don't know, circular sort of initial condition. Right?
Yeah. The initial condition has a circular symmetry, and because we imagine that if there is a pathogen, there is an activation of macrophages in the surrounding area. Okay, and we try to reproduce this activation, yes, but we really need this kind of initial condition with this symmetry, yes.
I see something interesting in the solution. I see two different things. So first of all, the symmetry is not always preserved, like the very central picture that you have here, like the rust that you have in the center, right? It's not like in the next picture on the actual skin. It's not, I guess, on the picture on the right.
Okay, here?
On the right.
Oh, sorry, here, sorry, see? Yes.
The very, I mean, the one from the skin.
Ah, this one, okay.
Right, so this one is not spherically symmetric anymore.
No, because here we use a domain, which is, linear, even if it is not the good word. I mean, in the skin, macrophages.
Right.
And also the other molecules are not free to diffuse, move freely. Okay. Okay. Here we use a simplification of the domain. Okay. We use a domain which is a simplification of what happens on your skin. This is the reason why here we obtain symmetry, and on the skin and in general in nature, you can't see this kind of symmetry.
Of course. The other question, again, sorry, I'm hogging the discussion here.
I'm happy to.
So again, in the center, so basically what you see, so again, I'm looking at the picture on the skin again, right? So you have this pronounced bump at the center of the rust, right? Which is not what you would expect if you had just diffusion acting on, being on the driver's seat, I guess, right? Because you start with something and then diffusion will try to normalize everything and just disperse everything, right? But the presence of this bump, I don't know what exactly it signifies in terms of dynamics. Do you have an intuition?
We have this bump in the center because of the chemotactic movement. Right. Because the chemotaxis tend to concentrate. Right. Okay. So we have on the one hand the diffusion that enlarges the rush, but the chemotaxis tends to aggregate.
Okay. It is very interesting. We should talk more about that.
Okay.
I'm mindful of the time, so let me thank you again.
Thank you.